All right. In this video, I'll be going over section 7.6. In section 7.6, basically, we'll be going over two important tests, which are called ratio test and the root test. Okay. All right. I want to start with theorem 7.34, which is the ratio test. Okay. Here is the statement of the theorem. Let sigma k goes from 1 to infinity ak be a series with positive terms and assume that rho is equal to limit k goes to infinity ak divided by ak plus 1 exists. Okay, we assume that this particular limit exists and we take that limit to be rho. Then here is the conclusion of the theorem. If the value of rho is less than 1, then the series converges. If the value of the rho is bigger than 1, then the series diverges. And if the value of rho is 1, then the test is inconclusive. That means we cannot apply this test if the value of rho is 1. If the value of rho is 1, our series may or may not be convergent. Okay. All right. Let's prove this theorem. I will start with part A. I'm going to assume that this limit is less than 1. Okay. Rho is the limit of this particular sequence. I'm going to assume that my rho is less than 1. Assume that rho is less than 1. And also notice that rho cannot be a negative number. Why is that? Look at the terms of this sequence, ak plus 1 over ak. This is clearly a positive quantity, right? Because all the terms of this series is positive. This quantity has to be a positive quantity. So you are taking the limit of a positive sequence. So this rho has to be a non-negative number. It cannot be a negative number, okay? So that means I can find, I'm going to take some r strictly between rho and 1. This is possible because rho is strictly less than 1. I'm assuming that rho is strictly less than 1. And also I know that this is bigger than or equal to 0. That is something that we will need later. But for the time being, we can pick such an r. I'm going to pick any r fixed in this interval, okay? And if I pick this r in this interval, notice that r has to be strictly greater than rho and strictly less than 1. Because I'm picking that inside this open interval. So r should be strictly greater than rho and strictly less than 1. Okay. Now, since this limit as k approaches to infinity, ak plus 1 divided by ak is equal to rho, and rho is less than r, there exists some large enough n bigger than 0 such that st means such that, okay, such that ak plus 1 divided by ak is less than r for all k greater than or equal to n. This follows from the definition of limit. Why is this true? Here is your interval, rho, comma 1, and r is strictly between rho and 1. Let's say r is somewhere here. Then we know that this sequence converges to rho. That means the values of the sequence are getting closer and closer to rho as k goes to infinity. Okay. That means by definition of the limit, we should be able to find some large enough n so that values of the sequence are less than r. All the values are in this region. If you pick your k to be bigger than n, okay, such an n exists, okay. So we have this. Now what I'm going to do is, this implies ak plus 1 less than r times ak for all k greater than or equal to n. I just multiplied this to the other side, okay. Since this is a positive term, I can do that without switching the inequality sign, okay. This implies that, this statement implies that, this is statement right here, a n plus 1 less than r times a n. And then if I plug in, this is true for all k greater than or equal to n. So I can plug in n plus 1, n plus 2, n plus 3, so on and so forth for k. Okay. So I should also have an plus 2 less than r times an plus 1. I'm replacing my k by n plus 1 in this case, n plus 1. Okay. But we know that this quantity is less than this one. So I'm going to replace my an plus 1 by r times an, because this quantity is bigger than my an. So I should get a bigger quantity. r times an. This is nothing but r squared an. Continuing this fashion, you should be able to see that n plus n is less than r to the power n times an. Okay, as you can see, if you have plus 1 here, it is r to the power 1 times an on the right hand side. If you have 2 here, this quantity should be less than r to the power 2 times an. Similarly, if we have a uppercase n plus lowercase n, it has to be less than r to the power lowercase n times an. Okay, so we have this sequence of inequalities. Now what I'm going to do is I'm going to consider the tail of the original series. Okay, so let me add a page here and consider the tail of the series. K is equal to 1 to infinity. K is equal to n to infinity. Ak. This is nothing but an plus 1 plus an plus 2 plus ... Okay, but we know that our an plus 1 is bigger than or equal to our an plus 1 is less than or equal to r times an. Okay, so I have this inequality. This has to be strictly less than. I'm going to leave my an as it is. I'm going to replace this an by r times an. My r times an is bigger than an plus 1. So I should get a bigger quantity. This inequality is correct. Okay, r times an. Similarly, I'm going to replace this term by r squared times an, because r squared times an is bigger than an plus 2. So I'm putting a bigger quantity there. Plus r squared times an plus ... As you can see, this is a geometric series. This is the starting term. By the way, the general form of a geometric series takes this form. Let me write it here. C plus CR plus CR squared plus ... Okay, this has the form of a geometric series given here. So this is a geometric series. This is the C, value of C, and this is the value of R, which is what we call the common ratio, right? And notice that here, let me actually write, this is a geometric series. And it converges. Since the absolute value of R in this case is R, which is less than 1. Remember, we took our R to be some positive number less than 1. R was a number less than 1. Of course, it was bigger than rho. Rho was a non-negative number. Okay, so R is some positive number less than 1. That means this series is a convergent series. Okay. All right. Now, by comparison test, we can easily see that this series also converges, because this series converges. Notice that the first term of this series, think about this series and the original series. The first term of this series is bigger than or equal to this one, because it's the same. So we can say that bigger than or equal to, nothing wrong with that. So this is bigger than or equal to the second term here. Third term is bigger than or equal to the third term here. So we can apply the comparison test. Okay, since this bigger series converges, the smallest series also converges by comparison test. By comparison test, this series converges. K goes from n to infinity, AK converges. Okay, but remember, we wanted to determine whether the original series converges, right? We wanted to determine whether the original series converges. Can we conclude that the original series converges if the tail part converges? Of course, yes. Okay, remember, the convergence of a series is determined by the tail part of the series. If the tail part of this is the tail part of the series, right? The summation of all the terms beyond and including nth term. Okay, so if the tail part converges, the entire series converges. This implies that K goes from 1 to infinity, AK also converges. Okay, this converges means this exists as a finite number, and if you add the first n terms to this series, you get the full series. Okay, the first n terms are going to be some finite terms. Okay, so you are adding some finite quantity to this to get the entire series, so you should get a finite sum. Okay, so we have this convergence. So we with that we complete the proof of part A. We showed that the series converges. Now, let's show that if rho is bigger than 1, the series diverges. Okay, so part B. Let's assume that rho is bigger than 1. Okay, if rho is bigger than 1, since this limit as k goes to infinity, ak plus 1 over ak is equal to rho, which is bigger than 1, there exists, again by the definition of limit, there exists some large enough n greater than 0 such that your ak plus 1 over ak is bigger than 1 for all k greater than or equal to n. Remember, this is the symbol to say for all. Okay, all right, how is this possible? We know that this sequence approaches to rho as k goes to infinity, but we know that rho is bigger than 1. Okay, here is the picture. Here is your value of rho, here is your value of 1, and we know that the our sequence ak plus 1 over ak is approaching to this value. That means after some large n, all the values of the sequence should be bigger than 1, right? That's the definition of, that's by the definition of the convergence of a sequence. Okay, so that means this statement is true. So that implies, this implies ak plus 1 is bigger than ak for all k greater than or equal to n. Okay, what does this tell you? If for all k greater than or equal to n, if this is true, what does that tell you? That tells you that this is an increasing sequence after k is equal to n. Okay, so this is an increasing sequence. That implies that ak is an increasing sequence for k bigger than or equal to n. And that implies limit k goes to infinity, ak is not equal to 0. Would you agree with me? If this is an increasing sequence for all k greater than or equal to n, and we also know that an is bigger than 0 because all the terms of our series are positive terms. So a uppercase n is positive, and that is the smallest term in this sequence, right? If you consider this sequence from k is equal to n to infinity, the smallest term in this sequence is going to be k a uppercase n because it's an increasing sequence. Okay, but a uppercase n is positive. If it is positive, this sequence cannot converge to 0. The limit as k goes to infinity, ak cannot be 0. It is not equal to 0. What does that tell you? Now, by divergence test, this series diverges. Series k goes from 1 to infinity, ak diverges. That's because this limit is not equal to 0. Okay, all right. That completes part B, proof of part B. Okay, now let's prove the last part. To prove the last part, we want to show that if rho is equal to 1, then the test is inconclusive. Or in other words, if you get rho is equal to 1, okay, to show that in this case, test is inconclusive, we need to find an example where the series converges with this limit, and an example where series diverges when rho is equal to 1. Okay, let's do that. I'm going to take these two series. The first series is sigma k goes from 1 to infinity 1 over k. The second series is sigma k goes from 1 to infinity 1 over k squared. Now let's compute ak plus limit as k goes to infinity. Limit as k goes to infinity, ak plus 1 divided by ak for this first series and for the second series. I'm going to compute the same thing for the second series. All right. How do I find this limit for the first series? Well, limit k goes to infinity, ak plus 1. ak plus 1 is 1 over k plus 1. Notice that your ak is this term, 1 over k. ak plus 1 is 1 over k plus 1. And in the bottom, you should have ak, which is 1 over k. And then doing the reciprocal rule and taking the limit, you will see that the limit is 1. Okay. Similarly, you can find the limit here. Here you get limit as k approaches to infinity, 1 over k plus 1 squared divided by 1 over k squared. This is going to be equal to limit k approaches to infinity, k squared over k plus 1 squared. What is this limit? To find this limit, of course, you need to expand this one. And then notice that the degree of the top and the degree of the bottom are equal. So you take this limit will be the ratio of the coefficients of the top and bottom. The coefficient of the top is 1. Coefficient of the bottom is 1. So the limit is 1. As you can see, in both cases, you get limit is equal to 1. But notice that from previous sections, we know that this is divergent. This is the harmonic series, right? Harmonic series diverges, but we know that this P series converges from previous sections. As you can see, here is an example where this ratio, the limit of this ratio is 1 in both cases, but there could be a convergent or divergent series. So that means the test is inconclusive. We cannot determine whether the series converges or diverges if this limit is equal to 1. All right. So this completes the proof of the theorem. Let's move on. Okay, now I want to go over this example, basically application of some applications of the ratio test. Let's go over the first part, part A. Obviously, we are going to use the ratio test. For ratio test, the first thing is you need to find ak plus 1 over ak, right? And then at the end of the day, you need to take the limit of that. First, let's find this quantity, ak plus 1. What is ak plus 1? This is your ak, by the way. This is going to be your ak. Then what is ak plus 1? You plug in k plus 1 there, right? 10 to the power k plus 1 divided by k plus 1 factorial. Notice that the factorial is nothing but factorial of k is 1 times, 2 times, 3 times, all the way up to k. The product of these numbers, okay? 1 times, 2 times, 3 times, up to k. All right, with that in mind, what is my denominator? This is divided by ak. Ak is, of course, 10 to the power k divided by k factorial. Now, if we try to expand this, you get, not expand, let's apply the reciprocal rule. Then this will become k plus 1 factorial times, this should be, pardon me, let me make this correction. This is 10 to the power k plus 1 divided by k plus 1 factorial multiplied by, you take the reciprocal, k factorial divided by 10 to the power k. Okay, notice that here this 10 to the power k and here 10 to the power k will be cancelled, but one power will survive. That means this will be equal to 10 times k factorial divided by k plus 1 factorial. What would you get if you simplify this? Notice that k factorial is this one, k plus 1 factorial is nothing but 1 times, 2 times, all the way up to k times k plus 1. You go up to k plus 1 in that case. Okay. Now, if you divide factorial of k by factorial of k plus 1, you get just k plus 1 in the bottom. You get 10 over k plus 1. Now, as you can see, you can clearly find the limit of this sequence, 10 over k plus 1. Okay, this is nothing but ak over ak plus 1. Let's take the limit. Now, limit as k goes to infinity, ak plus 1 over ak is equal to limit as k goes to infinity, 10 over k plus 1, which is clearly 0. As k goes to infinity, your denominator becomes bigger and bigger, and that is equal to 0. 0 is less than 1. So that means, what does that tell you? By the ratio test, series converges. Okay, so that's the conclusion. By ratio test, the series converges. Okay, all right, let's do part B now. Again, I'm going to apply the ratio test. For that, first I need to calculate ak divide ak plus 1, pardon me, ak plus 1 divided by ak. That is going to be this is ak plus 1. You just plug in, by the way, here, this is your, in the second case, this is your ak, okay? So ak, to get ak plus 1, you replace your k by k plus 1. This is what you get. And then in the bottom, you have ak. Your ak is precisely this one. Now we need some algebra here. 3 to the power k plus 1 divided by k plus 1 to the power 5 times k to the power 5 divided by 3 to the power k. As you can see here, we can simplify these two quantities. This is 3 to the power k plus 1. This is 3 to the power k. That will become 3 times k to the power 5 divided by k plus 1 to the power 5. Okay. Now, this is my ak plus 1 divided by ak in the simplified form. Now, let me take the limit. Limit as k approaches to infinity, 3 times k to the power 5 divided by k plus 1 to the power 5. How do you find this limit? Well, to find this limit, if you expand this one, you will see that the highest degree term is k to the power 5, right? in the top also the highest degree term is k to the power 5. Then what would be the limit? Limit is just the ratio between the coefficient of the highest degree term in the top and the coefficient of the highest degree term in the bottom. What is the coefficient of the highest degree term in the bottom if you expand this? It is just going to be k to the power 5, right? You can see if you expand this, it will be k to the power 5. Okay, so the answer is 3 over 1, which is 3. Okay, so this limit is 3. Notice that this is greater than 6, greater than 1. What does that tell you? By ratio test, this series, the original series diverges, right? If this is what we call rho, right? This is what we call the rho. Let me actually write it. This is the rho. Rho is bigger than 1, then the original series diverges. K goes from 1 to infinity. 3 to the power k divided by k to the power 5 diverges by ratio test. Okay, that completes that example. And this example is also very similar to the first two parts. So I will leave that as an exercise. All right, let's move on. Okay, the next example that I want to go over is this one. Show that the ratio test fails to determine the divergence of a harmonic series, this particular series, or the convergence of the P series. Sigma k goes from 1 to infinity, 1 over k squared. Okay, so we are asked to show that the the ratio test fails to determine the divergence of this series or convergence of this series. In fact, we are done with this example. Remember, when we proved the ratio test, when we gave the proof of the ratio test, we took these two examples, right? These are the two examples that we took. These are exactly the same examples that we have in that example. Okay, so we showed that if this summation, if you apply the ratio test for this one, not apply, if you compute this limit of this ratio, it is equal to 1. And if you compute the limit of this ratio, ak plus 1 over ak, as k goes to infinity, that is also equal to 1. But this series diverges and this series converges. So here, as we saw, the ratio test fails because this particular limit is 1. When that limit is equal to 1, the test is inconclusive. Okay, test fails. All right, let's move on. Okay, the next theorem I want to go over is theorem 7.35, the root test. Okay, here is what the theorem tells us. If let sigma k goes from 1 to infinity, ak be a series with positive terms, again, with series with positive terms, and assume that rho is equal to this particular limit. Limit as k goes to infinity, kth root of ak is equal to limit as k goes to infinity, 1 over kth power of ak exists. We assume that this limit exists. Then here are the conclusions. If that limit, which is what we denoted by rho, if that limit is less than 1, then the series converges. And if that limit is greater than 1, then the series diverges. And if that limit is equal to 1, then the test is inconclusive. We need to find another test to determine the convergence, okay, if rho is equal to 1. All right, again, the proof of this theorem is also very similar to the previous theorem that we proved, proof of the ratio test. So I'm not going to go over this proof of this theorem. Let's go over some examples, okay. Here is the example that I want to go over. Use the root test if appropriate. This is very important. You need to determine whether the root test is appropriate before you start doing the problem, okay, to determine the convergence or divergence of the following series. These are the three given series. We need to use the root test if it is appropriate. So for what examples do you think the root test would be appropriate? Okay, here is the rule of thumb. If factorial or factors of factorial are involved, root test is not going to help you often. Okay, so in this case, if you look at the first example and the third one, as you can see, factorials are involved, right? This is 2k minus 3 factorial. This is k factorial. If factorials are involved, then root test will not be appropriate. Okay, root test is appropriate for series which involves with exponential terms. As you can see, this series involves with exponential terms. As you can see here, you have exponent, some sort of exponent. Here also some sort of exponent, right? So if exponents are involved, then the root test might help you to determine the convergence. Okay, so this is the only example that we can use the root test for in this case. Okay, so let's try to apply the root test for part B. Okay, to apply the root test, I need to calculate this limit, right? Rho is the limit as k goes to infinity, kth root of ak. Notice that in our example, our ak is this one. This is ak. So let's try to find the value of rho. Rho is equal to limit as k goes to infinity, ak to the power kth root. Okay, kth root of ak. Ak is just 3k, 3 to the power k divided by k to the power 5 to the power 1 over k. That's what we mean by kth root. Okay, kth root means ak to the power 1 over k. So we need to calculate this. Now, applying the power to the top and bottom separately, we get limit as k goes to infinity, 3k to the power 1 over k divided by k to the power 5 to the power 1 over k. This simplifies to 3. In the top, clearly you have 3 because if you multiply k by k 1 over k, it is just 1. 3 to the power 1 is just 3. Divided by k to the power 5 over k. This can be written as, oh, by the way, I'm forgetting the limit here. So let me put the limit. Okay, so I have the limit here. And of course, if you simplify this, I can rewrite this this way. Okay, k to the power 5 over k is same as k to the power 1 over k to the power 5. But it is the same because if you multiply these two together, what would you get? You get this back. Okay, I'm just rewriting this expression in a little bit different way for a reason. Okay, you will see why. Now I can take the limit of the top and bottom separately. Limit, if I take the limit of the top, of course, it is going to be just 3, right? 3 is a constant. So the constant will stay as it is. And then in the bottom, you have limit as k approaches to infinity, k to the power 1 over k to the power 5. What is this limit? 3 divided by, remember from section 7.2, we know that limit as k goes to infinity, k to the power 1k approaches to 1. Okay, so this will become 1. 1 to the power 5 is just 1. I'll write 1 to the power 5. This is equal to 3. Okay, by section, this limit is by section 7.2. Okay, in section 7.2, we saw that this limit is limit as k goes to infinity, k to the power 1 over k is 1. All right, what does this tell us? Can we apply the root test here? As you can see, we calculated the value of rho, and the value of rho is bigger than 1 because the value of rho is 3 in this case. If the value of rho is bigger than 1, what is the conclusion of the root test? Series diverges, right? By root test, the given series k goes from 1 to infinity, 3 to the power k divided by k to the power 5 diverges. Since rho is bigger than 1, your rho was 3 in this case. Okay. All right, that completes that example. Let's move on. All right, let's go over this example now. Determine the convergence or divergence of the following series. Okay, so let's work on part A. Again, notice that all terms of this series are positive terms. So we can apply the ratio test or the root test in this case. The criteria for those two tests are satisfied. We need to determine whether we can apply the ratio test or the root test. Okay, so let's work on the first part. Notice that first of all, I'm going to identify the k term. Okay, so AAK is going to be 2 times 4 times 6 times ... 2k. That's your AK divided by 4 times 7 times 10 times ... 3k plus 1. Okay, this is going to be your AK. Now you can calculate AK divided by AK, the ratio. Okay, AK plus 1 divided by AK, pardon me. AK plus 1 divided by AK is going to be 2 times 4 times 6 ... 2k divided by times 2k plus 1, pardon me. Since your AK is this expression, to get AK plus 1, you replace your k by k plus 1. This k by k plus 1. Then you get, in the top you have this expression, and in the bottom you have 4 times 7 times 10 times ... 3k plus 4. If you replace this k by k plus 1, you get 3k plus 4. Okay, divided by AK. AK is just this expression. 2 times 4 times 6 times all the way up to 2k divided by 4 times 7 times 10 times all the way up to 3k plus 1. Okay, so this is equal to 2 times 4 times 6 times 2k divided by 4 times 7 times 10 times ... 3k plus 4 times, I'm applying the reciprocal rule here, 4 times 7 times 10 times ... 3k plus 1 divided by 2 times 4 times 6 times ... 2k. Now, as you can see, we have a bunch of cancellations here. Oh, this should be 2k plus 1, pardon me. Should be 2k plus 1. Because you have 2k plus 1 here. Okay. All right. Now you should see a bunch of cancellations here. So one set of cancellations would be here. These will be cancelled with this, and 2k plus 1 will survive. And here in the bottom, all these things will be gone with these things, and this will survive. Okay. So that means the remaining thing will be this is actually 2k plus 2. Okay, here it should be 2k plus 2, because if you plug in k plus 1 here, it becomes 2k plus 2. Okay, all right, so this should be 2k plus 2. Now this should be 2k plus 2 divided by 3k plus 4. Okay, now it's all about taking the limit of this expression to find the row. Okay, so remember, we are trying to apply the ratio test here. So let's find the limit of this quantity as k goes to infinity to see whether that is less than or equal, less than 1 or greater than 1. Of course, if it is equal to 1, the test is inconclusive. Okay. Okay, let me add a page here and find the limit as k approaches to infinity, ak plus 1 divided by ak. This is going to be limit as k approaches to infinity, 2k plus 2 divided by 3k plus 4. Clearly, this limit is 2 over 3. The degrees of the top and bottom are equal. So the limit is going to be the ratio of the two coefficients of the highest degree terms, that is 2 over 3. Okay. So notice that 2 over 3, our rho is 2 over 3, which is less than 1. That means the original series converges by the ratio test. Okay. If the rho value is less than 1, the original series converges. This implies that k goes from 1 to infinity. Actually, we have an kind of a implicit form for this. The given series, let me write, this implies that the given series converges by ratio test. Okay. All right. Okay, let's do part B now. In part B, I want you to verify that limit k goes to infinity ak plus 1 over ak is equal to 1. Okay, it is not hard to justify that. If you this is of course the k term ak, and then you find this ratio ak plus 1 divided by ak, and then you take the limit just like we did in the previous part, and you should be able to show that it is 1. Okay, that means rho is equal to 1. If rho is equal to 1, we know that the root test is inconclusive. No conclusion can be made if rho is equal to 1. Okay, so the root test fails. Okay, so what do we do if the root test fails? Well, you need to find a different approach, right? So for that, what I'm going to do is I'm going to study my k term. I'm going to take a closer look at my k term. 3 times, 5 times, all the way up to 2k minus 1 divided by 2 times, 4 times, 6 times, all the way up to 2k. Okay, what I'm going to do is I'm going to rearrange the terms of this. These are products, right? In the top you have a product, in the bottom also you have a product. So you can rewrite this ak in this way: 1 times 3 over 2 times 5 over 4 times 7 over 6 times, so on and so forth, 2k minus 1 over 2k minus 2 times 1 over 2k. I'm just rewriting the terms of this one. I combine this one, I separated it out, and then 3 over 2, 5 over 4, and then 7 over 6, 8 over 7, so on and so forth. 2k minus 1 over 2k minus 2. And finally, you have 1 over 2k. This term should be there. This is 1 over 2k. Okay. So now, as you can see, all these terms are bigger than 1. All these terms are bigger than 1. That means if I replace all these terms by 1, I should get a smaller quantity, right? This should be greater than 1 over 2k. Okay. I'm not going to touch this one. I'm going to replace all the other terms by 1. That means I'm putting something smaller because all these quantities are bigger than 1. Then I should get some smaller quantity in the left-hand side, right? I put 1 here, I put 1 here, I put 1 here. That means I'm making this expression smaller. So this original expression has to be greater than 1 over 2k. Okay. But here we know that if you consider this series, sigma k goes from 1 to infinity, 1 over 2k diverges. Because the harmonic series diverges. Here you just have a factor 1/2, right? You can of course pull out this 1/2. Even if you pull out this 1/2, you see that the sigma as k goes from 1 to infinity, 1 over k diverges. So this series should diverge. Okay, even if you multiply this 1 over k by 1 over half, it doesn't change the divergence property of this series. So this series diverges. Now by comparison test, the bigger series also should diverge. If you take sigma k goes from 1 to infinity ak, that should also diverge by the comparison test, because your ak is bigger than or equal to this particular kth term. Okay, this is the kth term of this series. So this, by comparison test, sigma k goes from 1 to infinity, ak diverges. The idea is that if the smaller series, this is smaller, right? This kth term is smaller than or equal to this kth term. If the smaller series associated to this kth term diverges, the bigger series should diverge. Okay? And notice that all the terms are positive in this series. Okay. All right. That completes that example. And with that, we conclude section 7.6. I'll stop there and I'll see you next time.